Hi everyone, I'm Lorenzo Bardoni, and I will present our paper entitled Sliding Down the Stairs, How Correlated Latent Variables Accelerate Learning with Neural Networks. We start from motivations, and I want to introduce the concept of higher-order cumulants, which are the properties of a probability distribution that cannot be modeled by a Gaussian distribution that can fit the mean and the covariance matrix of your data. But as we can see here, if you try to approximate images, natural images, for example, from CIFAR-10 with Gaussian distribution, you don't get something matching because you miss a lot from your data. And everything you miss are indeed higher-order cumulants. And indeed, neural networks to learn from a real-world distribution must be able to access them. But theoretically, it's very hard to understand how this can be done, because there are higher-order cumulant of rank P is a rank P tensor. And if you look at theoretical model of learning from a tensor, like tensor PCA, you find that you need a lot of data to retrieve one spike from a Gaussian tensor. And a number of samples n that grows as d to the p minus 1, which is too much to model realistically how neural network can learn from the higher-order cumulants. And so our motivation with this paper is to show that maybe in real-world data there are interactions between the easy part, the Gaussian part of the data, and the hard part, the higher-order cumulants part, that allow to learn faster. So we propose this model, which is we call the mixed cumulant model, and start as a classification task. So we have n data points, d-dimensional, x mu, and half of times they're distributed as a white noise, a white Gaussian noise, and half of times they have a spike distribution with 3 spikes. 2 easy, m and u, that are a Gaussian with different mean and a Gaussian with different covariance. And then there is one hard spike, v, and along v, the distribution is mean 0, variance 1, and it can only be distinguished by looking at higher-order cumulants. Indeed, there is a shape that's different with the bimodal distribution. So we're introducing the concept of latent variables. These are variables that model how the data behaves along these spike directions. So along m, there is a constant latent variable, but along u, there is a Gaussian latent variable lambda, and along v, there is a non-Gaussian latent variable nu. And they could be independent from one from another. So meaning that what happens along the easy direction is not doesn't transfer information on the hard direction, or they could be correlated. So there is a transfer of information between the hard direction and the easy direction. So we test the performance of a neural network in these two different cases. And so the procedure is the following. So we take a two-layer neural network and we train it with the full data, all the spikes. And then we test it with clones of our data with just few spikes. For example, the blue lines are with a clone that has only the mean spike. The green line is with both the mean and the covariance spike. The gold line is with the best Gaussian approximation of the data. And then the red line is with the full distribution. On the left here, we see the plot with independent latents. And as we can see, the cumulants are learned sequentially because the lines overlap at the beginning. And then at some point, you can see that the loss goes down and there is the lines don't overlap anymore. And as we can see, they overlap with the best Gaussian approximation for a long time. And only after many, many iterations, you can learn the higher-order cumulants part. The picture is different for the correlated latent behavior, in which we can see that you don't have this staircase behavior, but you have like a slide, and you can easily access the higher-order cumulants, and so the learning is accelerated. But why does this happen? So we studied theoretically on a single perceptron the dynamic. And the difference happens at the first stages of the dynamics. So if we expand the loss in this way, so as a function we have the overlaps with the weight of the perceptron with these our spikes p and nu in u, we can have the following approximated dynamic. And as we can see, there is this coefficient C11 that indeed depends on the correlation of the latent variables. And this is the leading coefficient for the equation of learning the R direction V. And is 0 when the latent variables are independent, and it's greater than 0 when the latent variables are correlated. So what's happening is that the information exponent of the R direction is lower thanks to correlation of latent variables. This was the main points of our paper. If you're interested in more details, you can check out the full paper. Thanks.